Let's take a look at what to do when integrating quotients. This is not as obvious if we think of all of our antiderivatives as what to do. But remember, when we're looking for using the method of substitution, we want to have the derivative of what we pick as our u present in the integral. Well, I notice that the denominator has a power of 3, and when we take the derivative of x cubed, we get 3x squared, which is what we have in the numerator, the x squared part at least. So usually we'll think of, if it's not obvious what the inside function is, to pick the part that when we take its derivative would be present elsewhere. So let's call the denominator the u, and off to the side we'll write that u equals 4x cubed minus 1. Taking the derivative, we get 12x squared dx. I do have the x squared and the dx, but I don't have the 12. So I'm going to multiply by the 12 and balance it by multiplying by 1/12. The 5, of course, is not needed in there, and because it's a constant multiple, I can take it out of the integral. So I have 12x squared dx, and all of that multiplied makes the du. So let's rewrite what our integral looks like. 5/12 on the outside. Integral of, all of the denominator was u, so 1 over u times du. You should be able to recognize this as our natural log antiderivative. So we have the 5/12 on the outside multiplied to the antiderivative of 1 over u, which is our natural log of absolute value of u, of course, plus constant of integration. Then we can substitute back what the u is, 5/12, natural log of absolute value of 4x cubed minus 1, plus c. So often when you have a quotient, you might think of making the denominator the u so that we end up with our natural log antiderivative. Let's find the integral of tangent of x dx. Now when I think back to all of the antiderivatives that I know, tangent of x is not one of them. It's not here on our list. So let's think about what we can do when we have a trig function. And remember, rewriting it sometimes is helpful. We can think of the integral of tangent of x as the integral of sine x over cosine x dx. How is that helpful? Well, remember when we talked about having a quotient where if we call the denominator the u, we might have its derivative in another part of the integral. And in fact, we do. If we call the denominator u off to the side, let's go ahead and write that u is cosine x. What is the derivative? Du is negative sine of x dx. And of course, we do have the sine of x dx, but we need the negative. So we're going to multiply by -1 and balance that by multiplying by -1, because -1 times -1 is +1, and multiplying by +1 doesn't change anything. So we have all of this part now. That is our du. Let's rewrite what that integral looks like. -1 times the integral of 1 over u du. And sure enough, now we're able to use that natural log. So this is going to look like -1 times the natural log of absolute value of u plus c, which is -1 times the natural log of absolute value of cosine of x plus c. Now, this is a way that we can see the integral of tangent x, because ultimately we don't want to have to go through this process every time. It would be easier if we just memorized the integral of tangent of x. Commonly, though, another way that you would see this is where we take the -1 to the exponent because of the natural log property, and let's see how that changes things. Cosine of x to the -1. And of course, to the -1 means the reciprocal of that. So that's the natural log of the absolute value of 1 over cosine of x. And what is 1 over cosine of x? Well, that's secant of x. So while this is a correct antiderivative for tangent of x, most likely, in most places, you'll see it written positively where it's the natural log of the absolute value of secant of x plus c. So whether you choose to memorize this version, or just doing it the long way, let's remember how to take the integral of tangent of x. Ultimately, let's make sure we memorize these 4 new trig derivatives that come from strategies like what we just talked about. The integral of tangent x is natural log of absolute value of secant x plus c. The integral of cotangent x dx is natural log of absolute value of sine x plus c. The integral of secant x dx is the natural log of the absolute value of secant x plus tangent x plus c. You might notice how that looks very close to the derivative of secant of x, where it's secant x times tangent x, of course without the natural log, but this one has a natural log, and we're adding secant x plus tangent x. So we like to look for some things that are like each other when we memorize things, and then cosecant x is very similar to that as well. Then, of course, thinking about how we take integrals of quotients when we have the denominator as our u and its derivative is in the numerator, that's going to give us the natural log function as the antiderivative. So here are some new antiderivatives that also we must memorize. Let's take a look at how to deal with this quotient, the integral of dx divided by the square root of 4 minus x squared. Now I might say this looks like the inside function for a composite function. So I'm going to try and say that u equals 4 minus x squared. Let's see what happens when I take the derivative. Du equals negative 2x dx. I do not have negative 2x dx. I can multiply by constants, but I cannot multiply by x's. I can say times x, but if I still have a 1 over x, what am I going to do with that? I can't pull out variables from integrals, only constant multiples. So while that was a pretty good effort, it is not going to work. Now I can also think of, what does this look like? Which of my antiderivatives does that resemble? And it kind of resembles this one, where I have a square root in the denominator and I'm subtracting an x squared. So it kind of looks like the inverse sign when I take the antiderivative. So let's make a note that this looks like doing the integral of 1 over square root of 1 minus x squared dx. Why do I want to write that down? Well, maybe I can manipulate this to look exactly like that instead of just sort of like that, since I'd only be playing with a constant. So let's see about what we can do. I'm going to rewrite this as the integral dx over, and I'm going to try factoring out that 4 so I can get the 1. So in the radical, I can factor out 4, and I'm left with 1 minus x squared divided by 4. I can always distribute to check. If I multiplied by 4, that divided by 4 part would go away, and it would look like that again. Well, now this looks pretty good, but I want to pull that 4 completely out of the radical. So if I take the square root of 4, now that's going to be the integral. I have 2 on the outside, square root, and I'm also going to rewrite that so it's a square, like that is a square, x over 2 squared. Now this is of that form. In fact, if I rewrite this, so instead of an x, it's a u, because it doesn't matter what variable is here, as long as these variables match, it might help us a little bit so that we don't think it has to be x squared. It's any variable expression squared. Any variable expression, like x over 2. This could be our u. So now let's try that. U equals x over 2, which remember is the same as 1/2 x, and then we'll take its derivative. Du is 1/2 times dx, and look at that, I do have 1/2 times dx. So all of this part right here is my du. Let's rewrite this integral now more simply as 1 over All of this part did not get substituted, so it's still there. Square root of 1 minus u squared, and then times du. And now I do have what I thought it looked like. So now I can apply the inverse sine antiderivative. I get inverse sine of u plus c, of course, and then I do my final substitution back to what x is. Oops, it wasn't that one. It was down here. Good thing I crossed that off so I didn't try to use that again. This is the u that I'm substituting. So inverse sine of x over 2 plus c.